Hello. Yeah, it's great to be here. I think I've been to two in the past, and at one of them we actually presented Stoffel when it was like internal at HashCloak, but now we've like spun it out into a separate company, and we've been like building it out for quite some time now. So it's like super great to be here. So yeah, today I'll cover what you kind of need to think about when you want to build ISAs and VMs for MPC. So I'll just like set some background first. So today, like, there's sort of two major things going on in computing in general, like distributed systems. We've kind of like settled on different kinds of architectures and approaches, whilst like this new thing called like programmable privacy is like coming to the forefront. Right, so like what is the state of distributed computing today? We have like the basic client-server model, service-oriented models, blockchains, etc. But they come with like a lot of limitations around like trust boundaries, privacy, centralization risk. And then while that's ongoing, we have programmable privacy that like kind of solves a lot of the problems that we saw in the previous slide. And the sort of programmable privacy isn't just like one thing. There's like a bunch of different tools that exist to sort of solve it, right? So I think most people here know what ZK is, has the most advanced tooling, but it sort of limits what you can do with private data. T tooling is probably also like getting there as well, but there are a lot of concerns around hardware risk, supply chain attacks, and so some people don't feel comfortable storing all of their private data within TEs for those reasons. This FHE that's also like very popular, but it's still very slow. A lot of companies have popped up to just like invent new hardware to like run FHE compute. But we have this thing called MPC that sort of gives you a lot of the same properties as FHE, but is a bit more practical. And so today we'll talk more about MPC is like a programmable privacy primitive today. And then just the state of like computers in general, like how we've been sort of building hardware for computers, right? So most people have a computer in their phone, and it's usually just on a single device, right? Most of it is like based on some form of like x86 architecture, but then there's like newer architectures that are coming out, like RISC-V, and then there's even GPUs that are still just like a singular device. And then there's some that are sort of optimized for distributed compute, like Beam. Has anybody like heard of like Erlang or Beam? That's like optimized to like run on like a single runtime, but like multiple nodes. And then there's some that are even optimized for certain forms of cryptography, like encryption. Like HSMs, like banks use these. But none of these really capture both distributed systems and programmable privacy. And so today we're going to talk about like how this works in MPC. So just as like a really high-level overview of MPC, we'll go into like more details later. It's a way to basically computer function as a group without like trusting some external party. So you see Stoffel here. Who's the real Stoffel? The function is to determine like who's the imposter or who's the real Stoffel. And it's commonly used in settings where like everybody distrusts each other. And what that means sort of depends on the setting in which you're deploying it in. This is very vague, but I'll go into like more details later about what exactly we mean by those terms. But just to like set the stage of like, if you want to use MPC today, what you're kind of forced to deal with. As a developer, you might like read some papers, you might encounter the word circuits, but you're not really writing circuit programs for the most part. If you use like a regular general purpose language, you're most likely dealing with like random access machines. But then once you like go further and really look at what's available to you today, you'll see APIs, you'll see DSLs, and then you're like faced with the decision to go even further, and then you'll see after that's all academic software to like use more interesting MPC stuff. And so like the state of using MPC is still like very early. Even though this academic software has been existing for a long time, it is deployed to production to a certain extent. For a lot of this because like there's a huge demand, but nothing exists really to alleviate that demand. And so like how can you reconcile the way people program today, right? Like any programming language that you use today is based on like this RAM model of computation and not circuits. But there's like a lot of optimizations that you get from running circuits in speed, and how do you sort of reconcile that in this like MPC environment. And the goal of today's talk is to sort of start at like not as close to the hardware, but as close to the hardware as possible, like instruction sets architecture, but that are designed to work with MPC, and to start sort of thinking about how can we make MPC more accessible and performant for developers. Yeah. So quickly, what's an ISA? If you know like a little bit of computer science, it's like the actual like set of instructions that your hardware actually runs. In this case, it's all going to be software. Maybe hopefully in the future we'll get hardware optimized for MPC, but right now it's all software. And then the VM is what actually like implements on top of a ISA, like implements the actual like instructions and how their process takes in a program, etc. So like the main distinction is like one is the specification and one is the implementation. So in more technical terms, so I gave like a very high level overview of MPC before, but this is a bit more specific. So you have a set of end parties that want to compute a function over some input x, but x is not known to any of the parties. And the nice thing that you want out of this is that from each other, you get privacy, right? So concretely in this example, we have 3 Stoffels. Which one is the real Stoffel? Every Stoffel has a set of inputs that they have as proof that they're the real Stoffel, but they don't want to reveal that information to each other, because like what if you reveal some information to the fake Stoffel and now he can like pretend to be the real Stoffel? And the way that's done, there's like these different kinds of like security notions for like how to build these sort of kind of fake Stoffel protocols, right? So there's sort of 2 angles over which we define security in MPC, and this defines sort of how you actually do the operations for computing f of x, and it does affect sort of what considerations you want to take into account when designing ISAs for MPC. So quickly, passive just means that like one of the Stoffels here can just like observe everybody going through the protocol, but doesn't actively do anything to stop the protocol from running, or some other like malicious behavior. Active just means that one of the Stoffels actively tries to like mess with the operation of trying to determine who the real Stoffel is. And then covert is, which this is not like a great example to show, but maybe one of the Stoffels will like cheat only if they know they can't get caught. In this case, there's only 3 of them, so it'll be obvious like if one of them gets caught. And then there's like over how many, what proportion of the parties are, being honest versus being dishonest, and that affects like how you design these protocols. So in this case, it's only 3. So you can design a protocol for determining who Stoffel is, either by assuming like 2 out of the 3 are honest, or by assuming just like one of them is honest. So the main ways to represent MPC computation in literature is via circuits. So arithmetic circuits, I'm sure everybody is very familiar with this. Binary and garbled circuits, and then mixed circuits where you kind of combine both. So very quickly, arithmetic circuits represent polynomials. You get 2 operations, addition and multiplication. And you mainly operate over like rings and fields. And you can like sort of represent any reasonable like polynomial approximation using this. And it's really great for like linear computation, addition, subtraction, stuff like this. Binary and garbled circuits are more closely like modeled after your regular circuits that you'll see in computers. And instead of having bits, you have like each bit is encrypted. You can do like the regular operations like XOR and AND. And these are really nice for nonlinear computation, like doing conditional assignments and stuff like that. And then there's like this nice thing in MPC that we call mixed circuits that combine both. So you can have MPC programs that are really highly optimized for linear computation, but then when you need to do some nonlinear computation, you can switch to binary circuits. And when you need to go back to linear computation, you can switch back to arithmetic circuits. It has a very high overhead, so it's heavily use case dependent. But for those use cases, it tends to be quite performant compared to just using a polynomial approximation for an if statement, for example. So fundamentally, the nature of MPC computation is such that you're basically operating over either shares or doing oblivious transfers. And these are inherently distributed objects that you pass around to other people in your network. And these objects have specific properties for shares and for encrypted bits for garbling. Addition is free, and by that we just mean that you don't need to send somebody else something in order to do A plus B, which is nice. That means if in your program you need to do an addition, you can just do it yourself, and you don't need to rely on somebody else. But when it comes to multiplication, now you need to incur latency. You need to talk to somebody else, especially in the case of preprocessing protocols. You need to generate preprocessing material and then share that with other people. And then when you need to do a multiplication, engage in a communication protocol. And this all happens over rings and fields. So this already sort of leads us to trying to think about different sort of instructions or architectures that might be amenable to the nature of MPC computation. So what makes ISA designed for MPC harder? So the first one is access patterns, right? And then the second one is complex control flow, if statements, loops, functions. And then the last one is that you're inherently in a distributed system. You're no longer on just one machine. So I'll go into more details. So access patterns I mean by accessing arrays, data structures that are important. This is what makes programming pretty powerful. One of the things that makes programming pretty powerful, you can store things, you can access them. But in MPC, you can't just access them. You have to consider, sure, the elements of this array, they can each have secret shared elements. But if you reveal what you're accessing, then that gives somebody a lot of information about what you might be computing, right? So this is there are many options for solving this. ORAM and garbled RAM are the main options. There's also special purpose protocols for this. One thing that you'll see commonly is also just leak the access patterns by saying okay, when you need to access an element in an array, you need to reveal it. You can't do any fancy ORAM things. So for the most part, in a lot of ISAs, this is actually a solved problem because there's a lot of off-the-shelf options for it. The next one that's also pretty hard to do is control flow. So if statements, branching, for loops, while loops, stuff like that. This is actually pretty hard because if you branch, then that reveals what you're doing, right? If I can run a program and look at what it's happening, but I don't have access to the problem, then I can say oh, okay, most likely that this if statement happened and not that if statement. So in practice, what ends up happening is you need to run both branches in order to not reveal what's happening. And so this is the actual hard part. And different ISAs sort of solve this differently. But the main way that it's solved is by actually just running both branches for the ISA, for the MPC compute. And then the last bit that's also pretty solved, but I think it's kind of underrated, is that you're inherently in a distributed system. What you're building for is inherently distributed. every network device that's participating in MPC network holds a piece of it. It doesn't hold the whole part of the state of what you're trying to compute. And this is sort of what distinguishes MPC from a lot of the other programmable privacy primitives, is that you have to design from the perspective of every node is a part of a single runtime, as opposed to every node running their own runtime and then talking to each other. And that's how normal computers sort of work for the most part, is that they each have their own runtime, and then they have to like learn to talk to each other. But the learning part isn't really like learning. It's more that like we design protocols to enable computers to talk to each other. Whereas like here, you just have to do it from scratch and like consider that when you're building the ISA. So general approaches for actually like, designing ISAs for MPC that you'll see in the wild. So the most common one is to just take an existing ISA, but then you do CPU emulation within an MPC network. The next one is to like design a custom one and just do whatever you want. And the last one is usually to do some combination of both while trying to like balance the expectations that both like give you. So the first one, which is pretty common actually, is just taking an existing ISA that is like very familiar to you, but then you emulate like every portion of that instruction set within an MPC protocol. And specifically, that means like for a specific ISA, you have a CPU, and the CPU is built up of like different components. So you would specifically take the CPU and implement each of those components as an MPC program. So here I'm just showing off like the flow. Does this do something? Okay, yeah. So this is like the flow of what this would look like. So around here, you get like the actual program from like say MIPS here. Like you write your C program, you target the compilation to a MIPS bytecode, and then you run the MIPS bytecode within like an MPC toolchain. This bit, right, distributed state across MPC parties, that's where you do the computation, the emulation. And you're doing that with a program counter that's also secret shared. So you're doing the step for every like MIPS instruction until the end. And like that incurs like a very large overhead because you clearly have to go through like every instruction and perform like a separate like MPC protocol. Obviously it composes all together, but it's like pretty resource intensive, especially if you have like a really large program. But the nice part is like you don't have to like teach a programmer a new programming language. The next one is basically just invent a new ISA for MPC. And like the world's your oyster here, you can really do whatever. But in general, what you kind of see is that there'll be specific opcodes for operating over specific MPC constructs. So you can like have shares directly as a first-class citizen. You don't need to have your ISA operate over something that's a bit lower level. You can have opcodes that are specific MPC protocols themselves and have them be more expressive over just like being like a load or just an add instruction. It can be like a concrete example can be, it can be like a zero knowledge proof. There are some MPC protocols that require zero knowledge proofs, like special purpose zero knowledge proofs in order to ensure like active security. And instead of like having to re-implement that from scratch as you would in an existing ISA, you can just have an opcode that does that for you. And the nice thing of being able to do this is you can take into account this distributed nature of MPC and ensure that all the machines that implement this ISA only hold part of the state and are able to like directly communicate with each other in order to like do the computation. But then the main downside for this is that like you're inventing a new computer, and so you need like new tooling to make that work. Either like a DSL, adapt existing tooling, whatever it may be, and then like the flow is more or less the same. Where is this cursor thing? Okay, the flow is more or less the same. You have like some DSL or high-level language. It compiles down to some R, but then you execute the instructions as you would expect any computer to execute. You just expect this to just be faster because you don't necessarily have like a secret shared program counter. And then the last one that's also like becoming more popular is to combine both of the previous approaches. And the main way this is done is that for the existing ISA, you kind of extend like the tooling, but then for the for the custom portion, you just have like base ISA that handles all of the MPC specific tooling, and then you use like special purpose MPC protocols to sort of make sure that between the ISA, not old, but like the off-the-shelf one composes well with the base one. And you still do like CPU emulation over like the existing ISA, but you've like delegated like a lot of the stuff that makes it expensive off to the base ISA. And so you kind of get best of both worlds where you can reuse existing tooling. Obviously, you still need to change some stuff, but it's like more amenable to like what people are used to. Yeah. So the implications of this is, yeah, I've said this multiple times. You're getting a new kind of computer. Tool chains will need to be adapted in most cases anyway. Most likely, people will make their own set of trade-offs, and there'll be like DLSLs for this. I think the last one is like the most interesting implication. When it comes to like speed ups in cryptography, we always think about like better math and better hardware. But in this case, you can get speed ups from sort of translating your problem from a cryptography problem to a compiler optimization problem, which is pretty neat. We don't really do that very often in cryptography, I find. And that means like whenever somebody says MPC is pretty slow, you can say like, no, it's not. You can use compiler optimization theory, which has like 50 plus years of research. So where are we now? So yeah, ISAs already exist for this. They're just in a state of being academic and like hard to use. So they already exist. There's all sorts of them. These are just the names of papers and software that I've personally used over the years, and Stoffel has like only so much space in his globe. But yeah, there are many others. If you want to learn more, you can just come chat to me after. So yeah, this is the end. Basically, some takeaways. We can make MPC practical today by like designing ISAs that are like production ready to take into account like the way developers program today. There's also a really wide design space for like how you want to go about designing ISAs. And then the last one, which I just said, which is you can use compiler optimization theory to like make MPC much faster and rely less on like just cryptography. So yeah, thank you for listening. If you want a die-cut sticker of Stoffel, come to me after the talk and just tell me a use case of MPC I may not have heard of. And you'll get like a cute little sticker. If you want to learn more about what Stoffel Labs is building, there's a link there, a QR code. Yeah, cool. Thank you.
Awesome. Thank you so much, Mikerah. Challenge accepted on the sticker.
Really
we have time for probably one question. Is anyone in the audience, would anyone in the audience here like to ask a question of Mikerah based on the talk?
This is what they look like. Really cute sticker.
Okay, I have a question then. Yeah. So in certain MPC architectures, there's some assumptions around the relative strength of each of the parties. Does that impact how you would design an ISA at all, depending if you had like one very powerful party and then one kind of like someone meant to be a client, or is that independent of the ISA and considerations of how you design it?
So in the, so in like the garbled circuit, oh wait, I should be using this, sorry. So for like a lot of the garbled circuit-based MPC protocols for which like you're using existing ISA, and then you like extend it, they do take into account that like one party is like the garbler and does most of the work. So yeah, I would say the answer to that is yeah.
Thank you. And let's give Mikerah a round of applause.